The intro to Chapter 6 notes here are connecting some topics, obviously some inequalities that we just talked about, but it's also going to connect to some vocabulary that we talked about at the very start of the course, like continuous and discrete. And those skills are going to be kind of linked together here, okay? So remember the difference between continuous and discrete. Discrete means countable. Okay, you have a discrete number of kids, 1, 2, 3, 4. You don't have 2.5 kids, okay? So it's something that you count. Continuous means it's something you measure. Continuous is measurable. How much rain did we get? Well, it could be 2.5 inches, okay? So if it's something that you measure, then decimals are appropriate, and you probably use some sort of scale to measure it, whether it's, pounds or heights or whatever. If it's discrete, then it's something that you count, and you cannot use decimals or fractions, okay? So as we work through these, keep in mind, is it continuous or is it discrete? Okay, and our number line is going to look a little bit different for discrete items than it is for continuous items. Okay, and I'll show you what I mean by that. Mrs. James is hoping to have at least 6 grandchildren. Okay, so let's use G for grandchildren. Okay, so G is how many grandchildren Miss James wants, and we're comparing that to the number 6. If she wants at least 6 grandchildren, we know that we want G, her grandchildren, to be greater than or equal to 6. She's cool with 6 grandkids, or she would be cool with 7, 8, 9. She wants at least 6, so that means 6 or more. Now, notice this is going to be discrete. Okay, it's discrete because it's countable. She can count how many grandkids she has. You don't measure it. She can't have 2.5 grandkids. There's 2 or 3. She counts them. So it is discrete. Okay? Now that doesn't affect what our inequality is, but it will affect our number line graph. We put a 6 in the middle. 7, 8, 9 would be to the right. 5, 4, 3 would be to the left. Okay. Well, greater than or equal to 6, we would start at 6 and shade to the right. Okay? Because towards 7, 8, 9. But here's the issue. I can't color the whole line, because if I color the whole line, I would be coloring over 6.5. And she can't have 6.5. She can have 6 exactly, or 7, or 8, or 9, but she can't have the values in between. So when it's a discrete situation, you're going to color the actual whole number dots, but you're not going to shade the whole line in between. Okay? I am, however, going to shade the arrow to show that it would keep on going. It would go to 10, 11, etc. Okay? Now, number 2, to make a profit, Jeans R Us must sell each pair of jeans for no lower than $24. So let's use P for price. Okay, that's the price of the jeans. And we know 24 is our cutoff. Okay, so is P the price bigger than 24 or less than 24? Well, they said no lower. Okay, so think about prices that are no lower than 24. Well, it could be 25. 25 is not lower than 24, or 26, or 27. So we want the price to be greater than 24, not lower. Okay, think about that carefully. Now, what about equal to? Should we put an equal to on it or not? And yes, we do want the equal to, because if it's not lower than 24, that means it could be greater, but it could also be equal to 24. It just can't be lower. Okay? So P is greater than or equal to 24. Okay? Now, we got to decide if this is continuous or discrete. Well, can money be a decimal? Could jeans cost $24.50? Yeah, they could. That'd be $24.50. So this one is continuous because decimals are okay. And I'm going to write it this way just because I'm feeling like making a joke here. It's continuous because decimals make sense. Okay, decimals make sense here, so it's okay to have a decimal. That means it is continuous. Okay. Now, notice on my graph, 24 is in the middle, I'm going to put a couple numbers on each side. The grandchildren was discrete because you couldn't have halves. You had to have a whole number. So we only colored the individual whole number dots. But here, you told me it's continuous. So I'm going to put, my dot at 24, okay? But I'm going to color the whole line. I'm going to color the whole line, the 25 and the 26, but also the decimals in between, 24.5, 24.6, etc., okay? Now, in our little activity, our wording of inequalities in activity, we put a squared off bracket on the 24 and we color to the right. Notice here I'm putting a solid dot. Solid dot is just like a squared off bracket, okay? That means it can equal that number. So either way is okay there, all right? For that graph. Okay, number 3. To wrestle in the Mighty Mites division, a child must weigh between 35 and 45 pounds inclusive. Okay, now let's talk about that word inclusive. Inclusive means that it can equal that number. So that means the child who weighs exactly 35 pounds is fine to wrestle in that division. It includes the number 35. It includes the number 45. Okay? All right, so how about I use W for weight? And I know the weight of the child has to be in between 35 and 45. Okay? 35 is less than the child's weight. The weight is more than 35. The weight is also less than 45. The weight is in between those numbers. And because it can equal 35 or 45, I'm going to put equal to symbols on there. Okay? Sometimes I call these sandwich inequalities because the number is sandwiched in between the two other numbers. Okay? All right, now on our number line graph, we're going to have 35 here, 40, 45. I may put some numbers on each side. I may go to 50 and down to 30 here. Okay? All right, so I need to decide if I'm going to color the individual dots or the whole line. Well, these are weights, and weights are continuous because decimals are okay. A child could weigh 37.5 pounds. A decimal's okay. So that means I'm coloring not just the whole numbers, but I'm shading the whole line in between 35 and 45. And I'm going to put the squared off brackets because it does have the equal to on those numbers. If you use solid dots instead of the squared off brackets, that would be fine. Okay? My math lab uses the squared off brackets. That's why I do that. Okay? Okay, on the back here, for each of the following, they want us to write an inequality, then sketch two number lines. The first to represent discrete, the second to represent continuous. So the only difference between the two graphs is if it's discrete, we're just going to have individual dots for those numbers. If it's continuous, we're going to shade the whole line to represent all the decimals in between. Okay? They want us to draw both. Now, the phrases here are like what we did in our little activity where we translated the inequalities. All right, so no more than 4. And I'm just going to use x for the variable every time. No more than 4 means x must be less than 4, or it could be equal to 4. It just can't be more. Okay, so for the discrete graph, here's my 4 in the middle. And put a number or 2 on each side. This is saying less than or equal to 4, so that would be the number 4, 3, 2, etc., including the little arrow at the end. Discrete means only those numbers, not the decimals in between. For continuous, I'm going to put my same numbers on there, but I'm going to shade the whole graph. That is including all the decimals and fractions in between. Okay? So in both cases, I started at 4 and went to the left, but on the discrete, I just colored the whole numbers. On the continuous, I shaded the whole line. Okay? All right, more than 7. If x is more than 7, that means it's greater than 7. Can't equal it, because if it equals 7, it won't be more. Okay? For the discrete graph, I'm going to put a couple numbers on each side of 7. Now, when I get ready to color this one, I cannot color the number 7, because if I color the number 7, that would indicate that it had an equal here, but it does not have an equal. So that means the numbers I'm going to shade are 8, 9, 10, and the arrow on the end. Okay? Not the whole line, just those whole numbers. And I can't color 7 because it didn't have an equal. Now, on the continuous graph, I'm going to shade the whole line, okay? And I'm going to put either a parenthesis indicates that it did not have an equal, or some people put a hollow dot and shade to the right. Either way is okay. The hollow dot or a parenthesis indicates it did not have an equal to sign, okay? Let me point out, as we're doing these graphs, if I'm going too fast, feel free to pause the video, stop it, rewind as you need to, okay? All right, number 6, fewer than 8. If you have fewer than 8, that means you have an amount smaller than 8. You have less than 8. You can't have equal to 8, you've got less than 8. For the discrete graph, put a couple numbers on each side. For the discrete graph, I'm going to color the numbers below 8. So the 7, the 6, and the arrow to show that it keeps going. I'm not going to color the 8 because I did not have an equal to. For the continuous, I'm coloring the line as well because it could have a decimal or a fraction. And I'm either going to put a parenthesis on the 8, that's how my math lab does it, or you could put a hollow dot on the 8. Either way is okay with me. My math lab puts the parenthesis. No fewer than 6. Okay, well, if you have no fewer than 6, that means you have more than 6. You don't have fewer, you have more. You have greater than 6. Okay? Or it could be equal. It just can't be below. All right, for discrete, it was a discrete situation here. You would color the 6, the 7, the 8, the 9, and the arrow. Okay. The reason we're coloring the 6 is because it can't be fewer than 6, but it could equal 6. It could be more than 6 or equal to 6. Okay. If it's continuous, then I would put either a solid dot at 6 or a squared off bracket, either way is fine, to show that it equals, and go to the right. Okay. At least 12. Well, if you have at least 12, that means you have 12 or more. X is greater than or equal to 12. For the discrete graph, 12 in the middle, a couple numbers on each side. If it's discrete, we're just coloring whole numbers. So 12, 13, 14, etc. and the arrow. If it's continuous, then we start at 12 and we go to the right, and we do color the whole line to represent all the decimals and fractions in between. At most 3. Well, if it's at most 3, that means 3 is the most, 3 is the largest, 3 is the highest. Could be less than 3, or it could equal 3, but 3 is the most it can be. It can't go above 3. So for the discrete graph, I'm coloring 3, 2, 1, etc. For continuous, still starting at 3, still going to the left, but this time I color the whole line, implying all the decimals and fractions in between. 10 and 11 are very similar. Okay, they both say between 3 and 7. But notice number 10 says inclusive. Inclusive means include the number 3 and 7. So this is one of those sandwich ones. X is sandwiched in between 3 and 7. Inclusive means it can equal the 3 and the 7. Okay, if it's a discrete situation, how many kids you have, how many books you have, how many specific items that you count, how many pets you have, etc. So 2, 3, 4, 5, 6, 7, 8, and put those numbers on there. If it's discrete, then it's just the 3, 4, 5, 6, and 7, those individual dots, no decimals or fractions in between. If it's a continuous situation, then we still color the 3 and the 7, but we color all the numbers in between, all the decimals and fractions. So maybe this is, if an item weighs between 3 and 7 pounds, so 3.5 would be in between. Okay, so that would be a continuous situation. All right, number 11. Still between 3 and 7, but it says exclusive. So X is still in between 3 and 7. It's still sandwiched in there, but exclusive means it does not include the numbers 3 and 7. So I don't put the equal to signs. If this is a discrete situation, okay, that's only 4, 5, and 6. It does not have equal to's on the 3 and 7, so I can't color the 3 dot and the 7 dot. I can only color the whole number dots in between. So only the whole numbers 4, 5, and 6 would get colored. If it was continuous, 2, 3, 4, 5, 6, 7, and 8. Okay. It can be all the decimals and fractions. So 3.5, 6.8, etc. So I'm either going to put hollow dots at 3 and 7 and color in between to show that it's all those numbers in between, including decimals and fractions. Or some people like to put parentheses on the 3 and 7 and color in between. It does not matter to me whether you put the hollow dots or the parentheses. My math lab is going to put parentheses, but some people like to draw it with the hollow dots, and that's fine. Okay? Okay, this video is getting kind of lengthy, so I'm going to pause it, or I'm going to stop it here, and then I'll make a separate video part 2 for the second page. That way you can kind of take a break if that helps. Okay, thanks.